Hello, everyone. Today we are going to present our Capstone project, Accelerated Cloud for Artificial Intelligence. Let's get right to it. So currently, ML practitioners that are building large-scale solutions and production-grade models need to involve themselves into the nitty-gritties of cloud development. So this involves developing pipelines, maintaining and deploying models, and also gaining expertise about the different cloud stacks and understanding the different components so they can better leverage resources and stay within their budgets. This is where Asai comes in. Asai is a cloud-based framework that aims to solve this problem. It prevents this diversion of attention from the ML researcher, and it lets them do what they really want to do by itself taking care of resource allocation and storage and reducing any other developmental overhead. In previous versions of Asai, we have seen features such as ML lifecycle with data lakes, as well as Jupyter Notebook integration for ML. This year, we are bringing three new features: Spark tuning system, which is an automatic tuning framework that is aims to improve the job performance and resource utilization of Spark jobs. Cross-cloud caching system, which is a new caching layer that automatically adapts to different workloads and applications that work in multiple cloud environments and aims to reduce latency and cost. And finally, Job Profiler, which leverages historical job execution as well as ML characteristics to predict execution time and suggest efficient provisioning strategies. So let's dive deeper into the Spark tuning system. So why do we want to tune Spark? With the ubiquitous presence of Spark in almost everything data, it has become the first step in many machine learning pipelines. With the acceptance by the industry, some companies run up to thousands of jobs a day. The resources consumed by these jobs directly affect their job runtime as well as cost, and tuning this can easily improve the performance to cost ratios. The benefit of tuning this is easily realized at scale. But why is this hard? So the main problem on Spark tuning is that it requires cloud expertise. It's very iterative and time consuming, and you need to know exactly how much computer memory you need to run your job successfully. Sometimes even over provisioning can reduce your runtime. Even with some cloud expertise, the number of parameters you need to tune becomes a bottleneck because they often interact with each other. And there's a significant amount of human hours required for the whole process. So how do we aim to solve this? So we propose a tuning framework that aims to improve the job performance in terms of both resource utilization, execution time, and cost. And this is done through automating this process through using optimization techniques that work in a different parameter space. And we need this because really Spark default configuration does not get the job done. So this is the architecture of our system. A user starts with interacting with the system through the Asai SDK and submits a Spark job for training. For this job, the config generator generates a configuration based on heuristic formulas to define the baseline configuration and ensure the successful run. The tuning framework uses historical runs along with heuristics and search space optimization algorithms to determine a tuned configuration for that run. And the job launcher reads these configurations, starts the cluster, and submits the job. While the job is running, the metric monitor collects important metrics such as execution runtime, stage overhead, as well as data, and reports these back to the tuning framework for the next run. So let's dive deeper into what exactly this tuning framework does. So the tuning framework basically executes the tuning process in a process through an abstraction of an algorithm. And we have two broad categories of algorithms here: heuristics and optimization algorithms. Before we touch these, let's quickly dive into what Spark does with data. And if you see a full data set is broken down into partitions, and each partition runs on an executor that has limited cores and memory. Executors determine the amount of parallelism in a given cluster. So complete through parallelism means that we aim to have the number of data partitions exactly equal to the number of cores in the cluster. So we're doing all the runs in the complete access to the data in one run. Minimum number of partitions aims to model this partition size behind the amount of data available in each executor, so that we might not actually run in one parallel stage of execution, but we are not overloading the data, which usually results in IO costs or data splurries. Next, for search space optimization algorithms, in the last heuristic, we saw that we're trying to model the size based on the amount of data. What if we can lower it and run it in more than one stage of data and do them parallelly? In fine-tune executors, we try to determine the best configuration and use a greedy approach to look around the vicinity of that iteration to find the best cores and partition pairs that work for this job. Finally, I'll try to hand over to Ishwar, who will walk you through particle swarm optimization. Spoiler alert, it's the best one.
Thanks, Shantanu. Let's talk about particle swarm optimization. In this algorithm, multiple particles start over the search space and they collectively try to arrive at a region of local or global optimum. The algorithm itself doesn't provide any convergence guarantees, but we typically saw that in our experiments, they converge within around 20 runs. So let's look at the step taken by a single particle and how it moves. So this is the current position of the particle. It is determined by three components, the next position of the particle. So the first one is the particle's current direction, and the next one is the best experience position of the particle, which is basically uh, the optimal value seen by the particle in its history. And the third one is the global best position, which is the best position so far from all the particles in the swarm. And each of these components can be weighted differently, and adding them together, we get the new position of the particle shown here in red. In our specific case, when we performed particle swarm optimization, we took two input parameters, which is the number of cores and the number of iterations. And yeah, we still haven't talked about the metric that we try to optimize for, and we'll talk about that next. So here, ideally, when you're running a job, you would want it to run as fast as possible with costing as less as possible. But you know that this is not always the case. They often pull in different opposite directions. So we try to come up with a metric that tries to penalize a higher execution time as well as a higher execution cost. So as you can see here, it's inversely proportional to both of them, and we can get a single metric that can capture both of them. And next, we to validate our hypothesis and to prove the usefulness of our tuning framework, we developed a bunch of experiments. And yeah, let's do some analysis on the experiments we did to see what happened. So these results are from an extract transform load job that is typically seen in preprocessing for ML pipelines. And yeah, so some of these are the input. These are some of the input parameters that the user provides: the number of cores, the total memory in the executors, and the partitions of the data. And these are some of the output metrics that we measure from a running job: the actual cost, the total cost of running the job, the execution time, and the utility metric that we just defined. So these are results from a few different configurations from our experiments. As you can see, the lower ones use more vCPU and memory, but yeah. So what happens here is they take up only a slightly higher cost, but they provide a steep decrease in runtime. So this might be desirable for many use cases where, um, and this is also shown by our utility metric on the side. And these are results for another job that we ran. This is the PageRank algorithm for a social network graph, and the results are similar here. So we move on to comparing the algorithms that we actually run. So this table shows the number of runs, the total cost, and the utility achieved by each algorithm. As you can see here, some of them get a higher utility score, but they also take a larger number of runs. So to make this comparison easier, let's look at this on a graph. So here, the x-axis represents the tuning cost for each algorithm, and the y-axis represents the utility metric achieved. As you can see here, this is the exhaustive grid search. It performs really well in terms of utility, but it also costs a lot. And some of the simpler algorithms that we saw previously, they cost very less, but they are very restrictive in their nature, and they don't provide a very good utility. And the particle swarm optimization that we spoke about seems to hit the sweet spot by providing good utility at a low cost. So having worked on this project for the past year, here are some of our key takeaways from it. First thing is that it's not easy to tune Spark jobs. There seems to be no generic approach to solve this problem. And through our algorithms, while developing these, we saw that we are able to provide a good utility compared to a grid search by refining this utility metric that we saw. And also we saw that we were able to achieve this by tuning only a few parameters, but we found that these were the ones that were the most impactful. So like any scientific work, there's always more to be done. So we highlight some of the things that could be good next steps in this domain. For instance, we could explore other Spark configurations like different serializers and changing the memory fractions. We could also use compute or memory optimized machines by profiling a job and assigning machines specific to those. This brings us to the end of the first feature we added by this year, and Andy will talk about the next cross-cloud crashing project.
Hi. So For the cross-cloud caching project, so the problem we're trying to solve is that as organizations have started to store data across different cloud regions or providers, there's the need to access these kind of data. But accessing these kind of data are often really expensive due to the high data egress costs between regions. And if these regions span vast geographical distance, then they often incur high network latency as well. So to solve this, we propose use caching to reduce latency and cost. And based on some prior talks, some cloud providers are already thinking about doing caching for some of their services, but they're not widely adopted yet. But even if they do, their services would usually be proprietary and not really flexible because the users don't know how the cachings are done and they can't easily change it. That's why we are proposing a prototype caching framework that can do caching automatically. It's open sourced. It can adapt to different workloads. So for our fall development goals, we built on what we built in the spring semester, and we implemented packing for small data objects. And I'll talk about what packing is and why it's important. We integrated memcache and object storage into the caching system. We implemented a server client architecture, and we explored and implemented eviction policy. So why packing and what it is? So cloud service provider usually charge the user based on the number of operations they issue to their storage services. For example, number of get and put requests. If you have a lot of small requests, operations, then they can add up really quickly and become really costly. And if you have too many of them, then it can even cause throttling, which can significantly hurt your performance. So to mitigate this, we could aggregate small data objects together into a larger data blob and issue much fewer get and put requests, and we can keep the mapping for extraction later. So this is our overall design. So first, we implemented a client library that the user would import into their script and use the APIs provided. It will perform the caching underneath and interact with all the other components without the users even knowing. We implemented a metadata server that will keep track of the metadata. We have a memcache server that will store small data objects for fast access because they are stored in memory. So it's faster to retrieve. We have an access history database that will store the access history of cached objects for eviction purposes. And last but not least, we have the eviction function that will free up space in storage. So some more implementation details for cache consistency model, we use time to live. And for write strategy, we use write through. And here's the general workflow. So when a user request comes in, it will be handled by the client library. It will first check with the memcache server for whether the data exists. If not, then it will check the locally cached mapping to see whether the data is packed in one of the data blobs in local S3. And if so, how to retrieve it. Either returns the location of the data, it will consult the metadata server for the location of the data, and at the same time, it will check the local S3 in case the data is a large data object and not packed. Finally, if none of these return the location of the data, then it will then the data has not been fetched before, so the client library will fetch the data from remote and cache it accordingly. So in our overall architecture, we only have a single metadata server, which is what is like how GFS does it, because having a single metadata server makes maintaining metadata consistent much easier. But this raises the issue, if we have multiple clients accessing metadata server, then it could become a bottleneck. So to mitigate this issue, there are multiple steps that we took. So first of all, the metadata server would only handle metadata, so there's no actual data transfer between metadata server and client library. The metadata server will only tell where the data is to the client, and each of the individual client will be responsible for handling all the actual data transfer. And at the same time, the client library will do the packing locally and only sends the mapping information to the metadata server. So there's minimal data transfer between the client and the server. And another step we took is that the client will have a local cached copy of the mapping so that it could check with it first to reduce network costs to metadata server. And another issue is that since we're using packing for small data objects, the mapping information becomes really important because without it, there's no way we could retrieve the data back again. So how do we persist these important mappings? So first is that in each of the committed data blob, it contains a header and a footer that will contain all the information necessary to reconstruct the mapping from scratch. But to reduce the overhead, the server will periodically push a backup to the mapping to the local S3. So that the next time when it tries to reconstruct the mapping, it doesn't have to read all of the committed data blob. It only needs to read the data blob that are committed after the most recent backup. So to evaluate the effectiveness of our design, we constructed a set of experiments that will measure the job execution time and the cost to see whether our system can reduce those. So the three workloads we constructed deals with small objects only, a mixed workload with small and large objects, and the third workload that deals exclusively with large objects. And for the setup, the remote data are in EU, other job workloads will be done in US, and there will be 3 clients running the same workload concurrently, accessing the metadata, and each workload is run 4 times consecutively. So for the first workload, many small objects, this is the first run. So as you can see, when we use cache, it actually took a little bit longer than when no caching is used. This is because the overhead of populating the cache and transferring data from remote to local, storing them, and maintaining the mapping, etc. These overhead. But soon, as you could see, in subsequent runs, once the cache is populated and warm, the performance is much better than when no cache is used at all. And for the gray bar, it is when the cache is already in local S3, but the data is in local S3, but not yet in the cache. So the warm up is even faster in this case. For the mixed workload, it's a similar trend. So for brevity, we will skip this for now. More can be read in the final report. And for large objects, there's an interesting anomaly because in the first run, even when we're using cache, it took a less time than when no cache is used at all. This is because S3 offers a specialized API that can transfer data from one bucket to another really efficiently. So the time it took to transfer from remote to local and then read from local is actually less than reading from remote directly. But for subsequent runs, it's the same as the other workload. Once the cache is populated, then we get much better performance. And then we perform cost calculation for each of the workload, and it's broken down into different category of the cost. For example, the data egress cost, the API cost, and then the server cost, etc. More analysis is done in the final report. But the key takeaway is that in all of the workload, we can achieve significant cost reduction, regardless of what type of workload it is. So the key takeaways we get from our result is that caching can effectively reduce workload execution time and cost, at least for the 3 scenarios that we constructed. In particular, it drastically decreased the data egress cost, which is often the most expensive part. And there will be some overhead during the first run where the cache is warming up for some of the workloads, but we think the subsequent performance improvement would justify the overhead. And then last but not least, we explore and implement eviction policy because we do not want our cache to grow indefinitely because cloud storage does incur a cost. So for our Capstone project, we implemented a relatively simple one where it is deployed as an AWS Lambda function that's connected to our cache bucket. So whenever a new object comes in, it will calculate the total size of the bucket. And if it exceeds a certain threshold, it will evict all cache objects that are last accessed more than 4 months ago, which is a value we calculated that's based on the trade-off between data egress cost and the storage cost. And the Lambda function will use the access history data collected in our database to help determine which cache objects are last accessed more than 4 months ago. So for our future plan, first, our eviction policy is pretty rudimentary at this point. So we will want to explore more sophisticated eviction policies. And second, we would like to use spot instances instead of on-demand for more cost saving. But since spot instances could be evicted at any time, the recovery mechanism or consistency mechanism becomes much more important. And ultimately, we want to construct a system that can dynamically change cache configuration based on user requirements. So now let's go on to Chinda for his job profiler project.
Great. Thank you so much, Andy. So I will not talk about the job profiler. So in the past year, we have observed that SI users often submit very similar jobs in a sequential order, or they could be running the same script on different data set, or they are running the same code on using different hyperparameters passed into the code. But it could be a not very easy task for them to figure out a good configuration for each of their submitted job, even though they're similar. So what end up with is that they often use the same configuration for other jobs, or they could request much more resources like courses than that they can actually utilize. On the other side, on the SI side, like we have a lot of requests, and also we have different specialized notebooks, like compute optimized or memory optimized. But like if user does not specify where should we launch the node, where should we launch the job? We need more information about the job, and any improper handling of this could easily cause any memory error or exhausted I/O of the node within the cluster. So it would be great if we can estimate the resource needed for each submitted job. So previously, SI has already made the first approach to solve the problem, where the method was to train machine learning models to predict the execution time, even the code and also the configurations. Although the method shows some good results previously when the training data set is sufficient, but it suffers from huge training costs, basically. And also the black box nature of the machine learning algorithms makes it hard to understand and debug the method. Outside the world of SI, people have tried either model the execution of different algorithms, machine learning jobs mathematically, and feed them later statistically, such as in 2016, the Ernst model, or in 2017, the Paris model proposed. They first offline benchmark the different machine types provided by the cloud provider, and then do the online metrics collection when the job is executing, then do the pairing and the matching to see like which one are the best to schedule the job. So we are incorporating all the ideas. So in this year's SI proposed to solve a problem using a job profiler that leverage both the historical job execution records and also generated profiling jobs metrics in the case where there's not enough historical runs for the model fitting. So to provide a service that can actually classify jobs type and also its bottleneck, and also service to estimate the execution time and also the memory requirement required for the job, so we can auto-provision the jobs for the users. And as for how do we model the similar jobs, we use what's called template and trial. A template is essentially an abstraction of the abstraction that user and the site can use to generate similar jobs, where within the template, the name of the template, code, user ID, all the metadata of the framework are fixed, but the input data set and also the command options where the user used to pass the hyperparameters are variable. And so each generated job has its unique inputs and also command options. And one trial is the actual execution of each job, and where it contains the input file set, the command options, and also the VCP requested, memory requested, also all the metrics we collected during the execution. And this is the overall architecture. So we will only cover it on a very high level. So when the user register a template, all the jobs that submitted subsequently belong to that template will be tracked by the job monitor by aggregated metrics collected by the promise server we deployed on the cluster. It will collect the metrics to the job maintenance service in the job profiler. It is responsible for updating and creating the job profile stored in the job profile history database. And the data is used by the prediction service, also the job type classification service, to do the predictions. And the auto provisioner, when they get a auto provision request, it will send a prediction request to these two prediction services and get the response and make deployment decisions accordingly. So let's dive deeper into how does job profiler work internally. So as we mentioned earlier, each trial contains the execution metrics that we collect during its execution span. So such as like the CPU usage, the memory usage, also IO usage. Each one is collected in a period of 10 seconds, where these metrics are aggregated into an entity where we call performance signature. So they are either like the CPU utilization percentiles or the max memory utilized during the lifespan, and etc. And to classify a template, we aggregate first all the trials that belongs to that template, all its metric performance signatures. We pass it into a decision-making module where we use heuristics, many different heuristics to decide if the nature of the job. such as if it's single thread or multi-thread, if it's CPU bound or non-CPU bound, does it have an IO large, etc. And the job type will play a central role in later part. And for predicting, we have one for estimation for memory requirement. Right now, we are feeding a second degree polynomial function, and the only input is the data size. And for execution time estimation, we model the execution time as a product of two functions, f and g. F stands for represents for the compute power it provides from both the number of vCPU requested, also the machine type it requested on. And the G is the amount of workload by running that code on that data with that data size, and also all the hyperparameters and arguments passed to code. So both and FG are fitted using least squares right now, and for and essentially we're using different feeding strategies based on the job type right now. And for auto provisioning, when users submit a request to the auto provisioner, they provide the template ID, they provide the input concept, they provide the command options, and also a deadline, which is like at least what time they want the job to be finished, a budget, and also optimization goal. So the optimization service will generate a grid of candidates that will be passed to the job provider, and the job provider will predict for every row of the it generated. And for the execute, and also like it will check the job type of the template, where like for any undesired resource request, it will into that row, so that option will be ignored. And auto provision service, based on the predicted result, it will find the best of configuration to schedule the job. So to validate our proposed method, so we have designed 5 single node workloads to run experiments on. So they are the characteristics of the jobs are listed in the table, so they are very different from each other. And for each workload, they have their own space. And to run the job, we first run the jobs, where then we evaluate on a on-scene test user submission, where they are used to evaluate the memory estimation, the execution time prediction, also the job type classification. So the first workload consists of like the training and inferencing of a random forest model. So the possible hyperparameters are the max depth and also the number of trees. And the data size are varied from 150 megabytes to 600, where the test submission is listed there with data size 300. And so the job is classified as multi-thread, CPU bound, and not IO heavy, which agrees with the invitation. And also estimate the memory is also very close to the actual memory measured throughout 5 runs. The blue part of the table is the input to the job provider, which is sent by the auto provisioner, and the green part are the response. We see that the predicted execution time and also estimated cost is very close to the actual number we measured. And also the second workload has the results we're reporting here. It consists of training a XGBoost models and also a great amount of data processing that involves a lot of IO operation. The job type classification and SM memory are all accurate with the measured value, but the predicted execution time is very far from the actual measured value. We are basically greatly underestimating the execution time here. And the reason for that is the nonlinear behavior of the IO part of the workload, basically because of GCP. This bursting nature. So in our model, we basically model that as a constant portion, but it essentially is a variable. So that's why our estimation is wrong here. So some key takeaways is that in this year, we use the job execution metrics to classify the job types and also the model, the memory and execution time using linear models. So it works really well on CPU-bound jobs and also algorithms like random forest, but it's less promising on other types of jobs. So basically in the future, we'd like to investigate more models for non-CPU-bound jobs, also explore GPU jobs, distributed jobs, and also better scheduling strategy based on each job type. And what have changed to previous deliverables is that for Spark tuning, we have removed some optimizations, and for cloud caching and job profile, we redesign architecture than what we tend to do in Spring. Also, we have some other small changes. as for reflection, we felt like the integration into existing large system could take more time than you thought, and also you should like incrementally do your development and not try to solve the workhorse problem in the first place. So thank you so much. And now for questions. Yep. Anyone on Zoom?
Sure. So great presentation, guys. I think the three individual capabilities that you worked on are really important. Each one of them, I actually enjoyed listening to you present them. What I didn't get a feeling of is how these have been integrated back into the system, right? So you didn't necessarily talk about the process of doing commits and changing the code base and stuff, which is okay, but it felt a little bit more like three independent studies than what a presentation of a SI systems team would be like in the past. Okay.
Yeah.
So, but can I assume that all three of those capabilities have been committed to the main SI code base at this time?
Yeah.
Yeah, we have
Yes.
some hidden slides on that, which we didn't actually present.
Okay,
So,
great.
doc-
Yeah, no. So as long as it's all done, great. We don't need to go into the details.
So yeah, I think they all are committed, but like some of the work have not been merged to the main branch yet. So there's like
Okay.
they're in that branch right now.
So how it works is that we, the GitHub workflows automatically build our images for us, and we've made it such that it does everything automatic. So we need like approval for it to go ahead, and we're waiting on that right now.
Yeah.
Okay, great.
Yeah. And for mine, it's a separate like Python package that's kind of like a standalone thing. So it will probably start a new repo inside SI that's like a separate package that the user could import it into their script instead of like integrating to the existing architecture.
Yeah. Okay. Is Mash there?
Yeah.
Yeah.
Does he have any questions for you guys? Hey, Mash, great job with the team this year. Really good stuff.
Thank you. Yeah. So I have a question for the Spark folks. You went a little too quickly over the types of jobs and the optimizations that were suitable. Don't go back.
Okay.
What guidance would you give individuals who have a Spark job, given the optimizations that you were able to achieve for the variety of jobs that you studied? What would you tell folks?
So this is someone who just has a Spark job and wants to tune it. Right. So it really depends on how optimized and how much time you have before you need to make this model production ready. And by production ready, I mean run configurations that you know are not going to fail. So we have a range of algorithms. Some are like one shot where you do these heuristics and you reach a place where a job will run. It won't be the most efficient, but we know it's working and it'll get you to get the job done in close enough cost, but probably a little longer time than ideal. And if you have enough time, we'd say run all the algorithms. Each algorithm builds on top of the previous ones and kind of better fine tunes it. So even if you run all of them sequentially, currently all that we have, they will be faster than the exhaustive grid search.
So I guess my question is, from all the runs that you did you come up with a basic set of best practices that if you have this type of job, then you should probably worry about reducing the number of iterations, or you should provision more resources, or worry about caching the data? Do you have any kind of more generalized best practices that you could share with the audience?
Yeah, sure. So some of the things that we saw were like avoiding disk spills is the first thing that you should be looking at. Avoiding disk spills. So you have enough memory. The number of partitions should be such that each partition fits into the core of the executors and doesn't spill to disk because it exceeds the memory available. So that's one of the basic things that you need to keep in mind. And also that the number of the ratio of the number of partitions to the actual number of cores available should be an integer multiple, so that none of the cores are idle at any point of time. You have all of them working. So you need to set your partition size to be such that it fits into the course. And so say you have 4 cores and you partition the data into 6 parts. So the first 4 would run in one iteration, and the next 2 would run in the next. In the second iteration, 2 of the cores are idle, and you don't want that happening. So in most of our search algorithms, we made sure that we skip over all the other configurations where it doesn't make sense that you have 2 cores idle or few cores idle. So those are some things that we incorporated into it, and we're able to skip some of the search space.
It will be good in your report that you add a section that outlines your general findings from the experience that you have. Thank you. Andy, you quickly said caching is expensive, but it's worth it. I think that trade-off is one that we always battle with whenever we're considering caching.
Right.
Can you give us a feel for the cost performance benefits that we have here? Is caching 2x more expensive than if we were not to cache, or is it 1/10 the extra cost for us to get all of this improvement?
So in terms of performance, as we saw in the graph, the first run for some workload, not all the workload, warming up took around maybe like 20% overhead, but for the subsequent runs, like the job execution time is usually only like 10% when you don't use cache at all. So I feel like as long as you run it more than once in our current setup, you could get the cost justified.
Yeah, but the cost is, how much is the cost? You have a memcached server, metadata server, and a lot of data movement.
Right, and then I think I showed the graph earlier with the cost calculation. So since the job execution time is so much shorter comparing to no caches used, so if we prorate all the server costs and stuff, it actually costs less than using no cache at all, because the data egress cost is just so much higher than using the server.
Good, thank you. And Chanda, we only have 1 minute. So how would you improve the prediction of IO bound jobs? I know you put it in the future work section, but your prediction is off for this nonlinearity. What would you do to account for it?
So for IO bounded jobs, so my idea is like, instead of predicting the actual runtime for that, because if you have a very small disk, the GCP will limit your IO per second very soon after you writing a lot of operations. So instead of that, we are getting a better provision strategy. So we have a node pool specialized with like provision IO per second disk. So whenever we see that the job has a lot of amount of IO work, we just provision on that part of the disk, because I would assume or would expect with a very high provision IO per second limits, that portion will become constant again, because the GCP would not limit the IO per second for the job, so we can go back to the linear model. But it's very hard to predict the actual IO, how much time does IO cost if you just run it on very small disk, because you don't know how, because GCP does not have
So how would you model that? What's a good idea to model that? You're still accurate.
So skew accurate. I think the current formula would work.
What kind of formula?
The current linear model would work.
Yeah, but you just said it doesn't, because you have 30%.
Yeah, because we're running it on a very small disk, essentially. If we run it on a provision IO per second disk, I think the current prediction will be accurate.
Yeah, I guess where I'm trying to lead you is, I'd like you to think about that a little bit more, and not just add it in the future work section as something for the future work folks to think about.
Yeah.
You should also see the idea with saying, I would consider, modeling this nonlinearity using the following approach, so that we can still capture what is the cost under the different conditions.
Yeah, so basically you can add more parameters, like how large the disk is, and the IO per second thresholds. Yeah.
These ideas. All right.
Yeah.
Thank you very much. Well done, team.
Thanks, guys. Great job. We need to move on to the next team.
Stop recording.
Thank you. No, just quit.